Okay, trying again. I had to redo the recording because the first one didn't have any sound. So in class we did go over discussion one assembly file, and we didn't finish it. So in this recording, I'm going to go over the rest of the instructions and try to tell you, one by one what the instructions do. So if you remember, this one was moving an octal value, and if you execute that, that's basically going to put, as far as I remember, 1C into WReg0. Yeah, so this is the 1C value that we have. And here you can look at the sub.b, and I said this in class too, that when you use sub b, you're asking the compiler to treat the operands as byte values. So normally this is a 16-bit microcontroller, so normally whatever you do in terms of additions and subtractions are done in 16 bits, but here you're forcing it to use byte values. So when you say subtract this hex 33 from the value that is currently in W0, which is 1C, then if I don't do the .b part, if I subtract 33 from this 1C, 33 is greater. So the result is going to be something negative. So here you're going to have FF something something or FE something something, which would be a negative number in terms of a 16-bit value. By the way, one point that you should really be careful about is the exact meaning of these instructions like sub b. So when I say sub b and the literal or constant value 33 comma W0, do I mean 1C minus 33? So 1C is the current value in W0. So do I mean W0 minus this literal and the result goes back to W0? Or do I mean 33 minus 1C, or do I mean 1C minus 33 that goes into W0? So you have to consult the manual and make sure that you understand. I mean, mostly these are intuitive, but just to make sure that you're not, messing things up, just make sure that you check things and know what is being done exactly. By the way, one difference that I noticed here, so this is a Windows machine. I didn't, I wasn't able to record it on a Mac, but my Mac compiler, MPDAPX, would show VAR32-bit as 2 bytes, and here it would show it using a 16-bit, so it would only show it as 0017. The compiler, the Mac compiler, doesn't understand this definition that we did. Let me go up there. Yeah, so the Mac compiler didn't understand that this dot space 4 really means that the variable is a 32-bit variable. The Mac compiler only assumed that we are saying reserve a space of 4, but it didn't associate this space 4 to the type of the variable to var32-bit. So in my Mac compiler, when I said var32-bit down here, it just went ahead and used it as a word and showed only 0017. And if I wanted to know what is exactly stored here, like the whole 32 bits, I had to put down here something like 0x802 as the address, and then 802 would show me this 000, which is here, or see what happened. Very interesting. So now var32 is only showing you 2 bytes. Not, this is really crazy. Okay, so but that's a good point. I mean, essentially you're seeing the difference between 32-bit variables and 64-bit and sorry, 16-bit variables and so on. And in some cases you even treat them as bytes, which are 8-bit variables, not 16-bit. So when you say sub b 33 from W0, and by the way, just to remind you again, W0 is the same as WReg0 and the same as WReg. Now W10 would be the same as WReg10. It would not be the same as WReg. So WReg with no numbers is the same as wreg0 in the manual. So that this could be confusing, but just know that this is some backward compatibility. They used to call there was one special register, and that was called wreg in the previous versions of the PIC microcontroller. So that's how the name carried. So when I say subtract 33 from W0, see what happens. So I execute one line, and you get E9, right? E9 is a negative number if you look at this wreg as an 8-bit value, right? It's a negative number if you consider it 8 bits. But if you look at it as a 16-bit number, then it's 0089, and if you ask it, it would say no, the sign bit, which is the bit number 15, is 0, which means this is a positive number, right? So be careful what you're doing. Even though the result of this sub.b was negative as a byte, and that would also affect the N flag, right? The result was negative, so the status flag N became negative as an 8-bit operation. But if you look at the result of wreg0 as a 16-bit variable, it is a positive value. Okay? So if you do a branch negative go somewhere else, the branch would be taken because N would be looking at the last operation. And the last operation happened to be byte. And as far as byte is concerned, the result was negative. It doesn't look at the 16-bit value. So all of these status bits only act on the last operation and the context of that operation. Okay, now this one is also interesting. So you have sub.b var32 wreg. Now var32, variable 32, is a 32-bit variable as the user defines, right? And essentially what this line translates into would be sub.b 0x800, not with the number sign before it, right? So this would be treated as sub b 0x800, right? So when you say sub.b, you're just saying forget about the context. I don't care what 800 is, how many words I've allocated there or whatever. The microcontroller doesn't know anything about that stuff, right? The microcontroller would only see 800 here and not the symbol var32-bit. So when you say sub b, that essentially means go to address 800 and take this 17, and only this 17 would be involved in anything else that you do. So even if I put 5, 6, 17, right? The operation would not use that 5, 6, and it would only use 1, 7 to do its computations. And if I do that, look at wreg. It's 00E9, and essentially what happens is that it's going to change the E9 to 2E, and these two zeros did not change. So that confirms that you treated it as a byte variable. Okay, and then we have increment wreg12 comma wreg. Now, if you remember, we did use this inc and then one of the wregs in the very first examples that we did. I think it was even in template.s, right? So without the wreg. But if you look at the manual would say that yes, you do have increment, and it could be some register here. And then in brackets, it would say comma wreg. So basically means if you don't put wreg, it means by default the semantics of it would be increment the register, in this case wreg12, put it back in wreg12. But if you put comma wreg, then it basically means increment the value, don't put it back in wreg12, put it in wreg instead. And look what value wreg12 is. It's 1f. 001f, and it's incremented. It's going to be incremented and put in here, and that's what we get here. You're going to get 20, which is 1f incremented. Now in your code you might have 0x200, and I mean if you want to play around with these numbers, then feel free to do it, but essentially the original version of it had 800, which is the starting address for this var 32 bit. And this is essentially to show you that yes, you could have sub f. So in a manual, you see things like sub f, and f could be anything, not just these wreg0 through wreg15. And you could just go to any address available in memory, in this case 800, take that value and do the subtraction. And here note that there is only one f here, which implicitly means wreg is the other operand that you want to work with. And if you do this, if you do the sub, so take a look at wreg0, which is 0020, and var32, which is 5617. And again, this is important. When you say sub 0x800, the machine, the microcontroller, is only going to see an address 800, and it's going to assume that it's a word that you're dealing with, right? It doesn't, a word which is 16 bits, it doesn't know about your intentions of var32-bit to be a 32-bit entity. So it's going to only involve this 5617 in the operation, and you can see that it changed to 55F7, after you subtract this, the 0020, which was implicit. When you don't put anything, that means that, subtract wreg from this variable here. And note that nothing changed here at address 802, because if you want to change it, then you have to have another instruction that involves var32-bit plus 2, and we did that when we did the increment example, if you remember. Okay, so the rest of the code, and probably the TA went over the code in more detail from this point forward. And essentially, I said that the reason that you put this here is that sometimes you want to provide a switch for the user to press, and the rest of the program you want it to continue. So none of the incremental stuff down here is going to happen unless you break out of this loop. And this loop says bit test port A number 0. So you're checking RA0 for being 0. If it is 0, bit test if clear, right? If it is clear, that bit, then skip the branch. If it isn't clear, then go back up to main loop and wait here, right? And if you remember the keys that we have, the switches, you enabled pull-up resistor, and if you press the key, it's going to become 0. It's going to connect to the ground. Just to refresh your memory, when we were setting things up, where did we do that? Here. So we set tris A bit 0. And if you remember, if a bit in tris A or tris B is 1, that means that that bit is going to be treated as input. And we also set the pull-up resistors. So there is an internal pull-up resistor pulling up RA0 to 1, logic 1. And if you press the switch, then you're going to basically connect to the ground and get a value of 0. So this code is going to wait for the user to press the key to move forward. And essentially what you do is you put 0 into W0, you increment var32-bit and add C var32-bit plus 2. So if you remember, this is exactly one of the two methods that we used to do increment on a 32-bit variable. Right? The other way was to increment the lower word, which was var32-bit, and then say branch not carry after the next instruction, which was increment var32-bit plus 2. So refer to your notes for what we did here, but essentially this group of 3 lines is doing increment var32. And then you complement it. It's 1 complement. If you want to do 2's complement, you would say negate, neg. And the reason that you add W0 to itself, basically the first add W0, W0, W0 is multiplying it by 2. The second line is doing another multiply by 2, which means you multiply it by 4. In binary, that means you have shifted the value 4 bits to the sorry, 2 bits. Each addition, each multiplication by 2 is going to shift it 1 bit position. So you're shifting it 2 bit positions, and you want port B to show the stuff, show the value of VAR32 starting with RB2. And the reason for that is, the debugger that we have, the in-circuit debugger uses RB0 and RB1 for its purposes. So we need those pins not to interfere with what the debugger wants to do, and you do it on port B. And then you remember that this does give you 40 milliseconds of delay, and that's how you would pass parameters. By the way, this would be a good point to make here. We're going to look at this in more detail when we talk about the interfacing between C and assembly. But essentially, if you think about it, msex is a function and it needs a parameter, right? I mean, msex is going to do a loop of whatever that you put in W0 and call 1 millisecond function that many times, right? So in C, this would be similar to saying msex 40, right? And the standard that we used here was to pass this parameter 40 in W0. And that happens a lot, right? Suppose your group in a company is responsible for writing this main part of the program. And then there is another person or another group in the company who's supposed to implement that msex as a function. Now, they and your team should decide beforehand how you're going to pass the parameters, right? And if you only have one word to pass, you could just use W0 to pass it along. If you have 2 words or 3 words, maybe you can decide that we are going to use W0, W1, W2, or maybe you want to push things on the stack, right? Same thing goes when you have some result coming back, right? So in C, you might say A equals some calc involving variable B, right? Then your team and the team who's responsible for implementing calc might decide, you know what, we're going to pass the value of B into W0 when we want to call. Then we're going to say call calc. And calc, before returning, is going to put the result of the computation back into W0, and I'm going to copy the value of W0 into A, right? Now, again, if you are writing everything in assembly, then you pretty much decide any method that you want for passing parameters or passing the return values of the functions. But if you're implementing part of your project in C, part of it in assembly, which almost certainly is going to be the case, right? Nobody's going to write everything in assembly. Then one file in your project is going to be a C file, and the C compiler is going to compile that. Another file of it would be assembly. And then when you write a sentence like this in C, A equals calc B, then the C compiler that Microchip developed, that is going to use its standards. It's going to probably put B in W0. Maybe the return value happens to be on a stack, or maybe it's put back in W0. And this is going to what's going to happen if you have multiple input parameters and so on and so forth. Then you're forced to use whatever standards the C compiler is going to use, right? If you didn't fully understand this part, that's okay. We're going to come back to it, and we're going to do interfacing between C and assembly. Here, I just wanted to give you a heads up that people have to think about how to pass parameters, how to send return values to the caller that basically calls a function. All right, let's move on. I can pretty much skip the rest of this stuff. Let me just again give you heads up, a very brief intro on what this bracket W12 is. Now, this is called indirect addressing, okay? And the reason you need it would be clear if you consider this example. Suppose I tell you that I have 10 numbers stored at address 800, 802, 804, so on and so forth, right? And if I ask you to add up all of these values, you probably are going to do something like, move 0x800 into W0, followed by a bunch of, add 0x802, and put the result back in W0, add 804, 806, so on and so forth, right? And that looks silly, right? I mean, you have 10 values to add, and you're adding 10 instructions to do it. I mean, usually the more natural way would be to do loops. And it especially becomes ridiculous if you have 100 numbers to add, right? So that's not going to work. But the problem is you don't have an instruction that says change this 800 value itself. The 800 value is going to be hard-coded into the coding, the opcode that describes this variable. So you have two ways. One is to change the program memory and have a loop, but then, somewhere in the loop, make sure that you change this opcode into 802, 804, and so on. And this is doable. I mean, in the old days, people did used to do that, but it's very dangerous. And of course, I mean, consider the fact that your PIC microcontroller has a program memory that is flash-based. And if you want to write things into flash memory, it's going to be really slow. So this is absolutely not the way to do it. Another way to do it would be to do indirect addressing. So you can put W12 to be 0x800. And if you say the bracket here, the bracket means I'm not interested in the 800 value. I'm interested in going to address 800. And whatever value that you have there, which in this case would be 55F7, I'm interested in that. Put that into W3, or, involve that in adding to W0. And the nice thing about it is you can say increment WH12 inside the loop. And next time that they come around, this would be saying 803 or 802, 803, or if you want you can increment it by 2, and there is an instruction that says increment a variable by 2, so you could say 800, next time 802, 804, 806, and each time you're going to go to the memory location that is pointing to address 800, 802, 804, and you will be, each time that you're executing this instruction, you are in fact picking a different value from the memory. This becomes a little bit more clear once we look at the opcodes and how these assembly instructions translate to the stuff that go into program memory. But that's essentially what the indirect addressing mode is used for. And a line next to it, line after it, you have W11 plus 12. Now that would be useful for cases like this. So in C programming, for example, you might have an array A, and then you would say A index 12. And essentially, if you want to do that, then basically what you need to do is to put the starting address of A into W11 and then add 12 to it so that you move 12 locations in memory. And of course, I mean, this would be the byte oriented. If you want word oriented, you have to do plus 24, but we'll get to that stuff later. So just know that these addressing modes exist as well. And if you've looked at the manual, you've noticed things like W1 plus plus and minus minus W1 and so on in the indirect addressing mode. And these are interesting things that allow you in one instruction to both access the content of, let's say, memory 802 and advance that address to 804, 806, and so on. So we will dedicate some time, and I'll probably just do a recording on these indirect addressings, and let you work with arrays and strings of characters and stuff like that. Okay, let me end this video here. I'll do other videos on different stuff that we're going to cover. So hopefully this one will go through and we won't lose the voice. Thank you.